Hello folks, I am Georgios Papadopoulos and welcome to this introductory video on CoAP Architecture. Now this video is just one in a much longer series of tutorial videos on CoAP. So if that interests you, you should subscribe and check out the rest of the videos as well. CoAP stands for Constrained Application Protocol and it is defined in RFC 7252 standard. CoAP is a web transfer protocol with low header overhead specifically designed for constrained nodes and networks such as those that form the Internet of Things. In this video, we are going to start first with the IoT Protocol Stack, then we will continue with the CoAP Features and Terminology, and next we will go briefly over the CoAP Type of Messages, which will help us to follow the last part of this video, which is the CoAP Architecture. Let us now start with the TCPIP and the IoT Protocol Stacks in order to better understand where the CoAP protocol is positioned. In this video, we will focus on the 5-layer TCPIP protocol suite. So let's remind ourselves about the protocols at each layer. At the application layer, we have the HTTP protocol among the others. Then the two most common transport protocols are TCP and UDP. At the network layer, we have either the Internet Protocol version 4, IPv4, or IPv6. Next, at the data link layer, we have the destination and source MAC addresses. Finally, we have the physical layer or layer 1. This layer is most closely associated with the physical connection between devices. Basically, once the data arrives at the physical layer, it is then physically transmitted. IEEE 802.3 defines the physical and data link layers, medium access control or MAC protocols of wired Ethernet, while IEEE 802.11 specifies the set of MAC and physical layer protocols for Wi-Fi. Now, on top of the HTTP, there is typically very verbose web representation formats such as XML or JSON to structure the information. It is worth mentioning that the protocols at the two bottom layers are being standardized at the IEEE, while the protocols from layer 3 and above are being standardized at the IETF Standardization Organization. Now, by employing this 5-layer TCP/IP protocol suite, two or more typical computers may communicate to carry data from one to another. However, one issue with this protocol suite is that it has been designed for Ethernet and/or Wi-Fi based technologies that come with high bandwidth and packet sizes of maximum transmission unit MTU in the order of 1000 plus bytes, which is not realistic for Internet of Things. So what does it look like when we go from the classical TCP/IP enabled devices and networks to constrained devices and low power and lossy mesh networks such as Thread and 60s that are based on IEEE 802.15.4 technology for the data link and physical layers, and which come with limited bandwidth and support packet sizes in the order of 100 something bytes. Well, in order to anticipate this transition, IETF has designed and defined a specific protocol stack, often called the 6LoWPAN protocol stack. This newly defined 6LoWPAN protocol stack uses some of the existing protocols such as the UDP instead of TCP for the sake of simplicity. Then IPv6 instead of IPv4 is employed since there are not enough IPv4 addresses left. However, since the IPv6 header is much larger than the one of IPv4, a new adaptation layer, 6LoWPAN, was defined to compress the IPv6 header and, if necessary, to fragment the packet into multiple frames of 127 bytes. Furthermore, 6LoWPAN compresses the 8-byte UDP header as well. You can find the dedicated videos on 6LoWPAN technology on our channel. On top of UDP, the core working group at the IETF has defined the compatible with HTTP and efficient Constraint Application Protocol, or CoAP, which is a web transfer protocol with low header overhead specifically designed for constrained nodes and networks. The interaction model of CoAP is similar to the client-server model of HTTP. Finally, on top of the CoAP, there is CBOR, which is a binary data serialization format loosely based on JSON. CBOR stands for Concise Binary Object Representation. Now, combining the CBOR, CoAP, and 6LoWPAN protocols, we can get overheads down to just tens of bytes, which can be carried in constrained mesh technologies such as Thread and 60s that come with MTU of 127 bytes. Similarly, when we go from the 6LoWPAN protocol stack to ultra-constrained long-range LPWAN technologies such as LoRa and NB-IoT that support packet sizes in the order of tens of bytes, the objective of LPWAN working group at the IETF was not to design a new protocol stack in order to avoid potential interoperability issues. And therefore, as it can be observed, most of the protocols were kept, including the CoAP. The only change was to extend the 6LoWPAN compression and fragmentation mechanisms that was previously designed for low power and lossy mesh networks to LPWAN technologies. And this was achieved thanks to the SCHC protocol, which stands for Static Context Header Compression. SCHC is packet-oriented, or in other words, flow-independent, and a generic framework, since it can be applied to other protocols in addition to IPv6, UDP, and CoAP. Let us now to proceed with the second part of this video, which is the CoAP features. Before going through the main features of CoAP, let's check what CoAP is and what is not. Well, CoAP is a very efficient REST protocol which is suitable for constrained nodes and networks. It is specifically designed for machine-to-machine and IoT applications with constrained requirements. Finally, it is easy to proxy back and forth from HTTP. On the other hand, CoAP is not a complete replacement for HTTP, and it is not a compression mechanism either to save some bandwidth out of HTTP. Finally, CoAP is not restricted to the automation networks. Let us now look deeper at the CoAP features. First of all, CoAP, the Constraint Application Protocol, is an open IETF standard. Now, CoAP does have a scheme, CoAP:// or with security, which is CoAP://. These schemes come with default ports, the 5683 and 5684 respectively. CoAP includes strong security built into the protocol using DTLS based on the following modes: pre-shared keys, PSK, raw public key, RPK, and certificate. Then the typical bindings are to UDP, SMS over cellular networks, and to TCP. The UDP binding includes its own reliability, which is based on simple binary exponential backoff. Unlike HTTP, CoAP is completely asynchronous, and thanks to the use of UDP, a subscription can be built natively. Furthermore, CoAP supports built-in discovery mechanism. It also supports all the basic methods of the HTTP: GET, POST, PUT, and DELETE. And finally, it supports UREs, but it does it in a very compact binary 4-byte header with options. Finally, CoAP comes with the ability to do subscriptions and even block transfers of larger files. Let us now continue with the terms that are defined in RFC 7252 and which we will use later in this video. The first term is the endpoint. An endpoint is an entity participating in the CoAP protocol, and it is identified with a node or a host. Then there is the sender, which is the originating or source endpoint of a message. Next, there is the recipient, which is the destination endpoint of a message. Then there is the client, which is the originating endpoint of a request. And finally, there is the server, which is the destination endpoint of the request. Now, RFC 7252 standard also defines 4 types of messages, and that includes the confirmable, non-confirmable, acknowledgement, and reset. So the first message is the confirmable, and it is a message that requires an acknowledgement. Then there is the non-confirmable message, and it is the message that does not require an acknowledgement. The third message type is the acknowledgement. An acknowledgement message acknowledges that a specific confirmable message arrived. The fourth and the last message is the reset. A reset message indicates that a specific message, which can be a confirmable or non-confirmable, was received, but some state is missing to properly process it. Let us now proceed with the last and the core part of this video, which is the CoAP architecture. The Constrained Application Protocol is already very useful when we use it for communication between CoAP endpoints within a constrained environment. But it reaches its full potential by interworking with HTTP. The REST architectural style enables this through proxies, or more generally, intermediaries that behave like a server to a client and play a client toward another server. This one-to-one mapping between the two protocol stacks, the TCPIP and the IoT, makes it possible to interwork the two protocols via a proxy. Within the constrained network, CoAP is used, but elsewhere, CoAP messages can be translated into HTTP. It is also possible to bypass such a proxy and deploy CoAP end-to-end if cloud platforms support it. The interaction model of CoAP is similar to the client-server model of HTTP. Indeed, a CoAP request is equivalent to that of HTTP, and it is sent by a client to request an action on a particular resource identified by an URI on a server. If the response is immediately available, then the server will return it by carrying it in the resulting acknowledgement message. Now, if we are going back to the previously presented IoT protocol stack, logically, CoAP could be considered as two layers approach. A messaging layer employed to deal with UDP and the asynchronous nature of the messages, and the request responses layer that manages request-response interactions. And that's all, folks. Thank you for watching, and if you have enjoyed this video, you should subscribe and check out the rest of the videos on CoAP.